Hello, it's Keith here, and this is lesson 44 of the platform-specific series of my 650 assembly programming tutorials, and we're looking at the NES again, and we're going to have a bit of fun because we're going to play with an emulation of the NES Zapper, which is the Lightgun. Now, the NES Zapper is very basic, like pretty much all of the light guns, to my knowledge, were back in those days. Basically, it's got a trigger, which is just a simple switch, and it's got a light sensor with some kind of lens on it, which detects light in the direction of the screen, and it will detect a small area of the screen. So basically all of the intelligence of detecting what the gun is pointing at is down to us. We need to change what appears on the screen and test the light sensor to see if it's seeing light when we expect it to see light based on what's on the screen. So what we're going to do is we're going to play with this, and we're going to do 3 different tests. The first test is just simply reading the data. To read the light gun, all we do is read in from the joystick port. I'm assuming the light gun's connected to port 2, and there's 2 bits. One is the trigger and one is the light sensor, and that's what we're going to be doing. So we're going to read those in first and just see what they're showing. Then we're going to do a more advanced test, which is very much like the duck hunt game, where we see if the player has shot a target by lighting it up and seeing if the light sensor sees light and blanking the screen. And if the light sensor still sees light, well, the gun clearly wasn't pointing at the target. It's probably pointing at a light bulb, and the player's probably trying to cheat us, which is why usually that doesn't work on those kind of games. Never worked for me when I was trying to cheat anyway. So that's the second example, and the third one is the best I can do, at least, and we're trying to do what Operation Wolf does. Now, Operation Wolf tries to almost perfectly guess the tile that the gun is pointing at. It's not as good as the Sega Master System. Sega Master System has dedicated hardware and it's nearly pixel perfect. The NES can't do that, so all we can do is we can get an approximate line by just timing from the start of the drawing of the screen to the time that the light gun sees light. That will give us an approximate position vertically, and then we can then move a sprite across the screen until we see it, and when we do, then we know that the gun is pointing at where that sprite currently is. So that's what we're going to be doing. We're going to be doing 3 different examples. Let's go over to our source code and let's have a look. Now, one thing to point out is that today's example is, of course, using a light gun which is designed to work with a CRT screen. So if you're trying to use a NES on a TFT, it's not going to work. Also, I've only tested this on emulators, and I've only tested it on the Nestopia emulator because it's an optical technique. Maybe other emulators won't emulate it perfectly, but that's the best I can do at this stage. So that's what we're going to be looking at. And the other thing is, this example uses sprite drawing routines and tile map setting routines that I've covered in other tutorials. If you want to know how they work, see the Simple series. See the YQuest series is probably the best because that covered the hardware sprite routine and the tile map routine that I'm using today. It's doing an update during the NMI interrupt. So I'm not covering that today because otherwise this will be a very, very long episode. So I'm going to assume you know about that or don't care, or you can figure it out yourself, or you're going to watch my other tutorials, because if you're not, then I'm afraid that's on you. Anyway, so here's the start of our code here. We've got some variables to store our X and Y position for the scanning routine. We've got some stuff for the NMI updates to the hardware sprites and the tile map, and a few of the general things here. Now, the first thing we're going to look at here is we're just resetting the light gun Y because that is being used to trigger the NMI scan of the screen. We'll look at that later because that's not relevant to our first example. Our first example is this show stats example. This is the simplest example, and all this does is it shows in the value read in from the joystick port. Now we're loading in from 4017, which is joystick port 2, and we're going to read that in and we're going to show it to the screen. We're also showing a white area of the screen with this fill area with tiles routine, which is based on the Simple series. So we're going to draw a white block, and that's so we can test the light sensor and see what that light sensor sees, because we're going to need to understand that. Let's fire it up. Now when it starts up, it will it's scanning the joystick port and it will demand you connect a light gun. It's just so you know what's going on. And then if we just do input and we select light gun here, there we go. So you can see here we've got some text at the top of the screen. Now the accumulator here is actually what the light gun is seeing. So you can see here it currently says 48, and the important thing to understand is the light sensor, as you may have noticed, is actually scanning all the time, not just when we click our fire button. So basically if I point at the text, you will see it flicker as well, and that is why it's a bit tricky reading these light sensors, because this is my target, this white block here, but if there's anything else on the screen that might also misfire it. So you can see here, if I move the mouse over the white block, the bit 4 there, the bit 3 there will start flashing, going from an 8 to a 0. Now why is that? Well, because that's the light sensor, but why is it not constantly on? Well, although this TFT in this emulation, it looks constantly on, a CRT beam would be scanning constantly and its eye is too slow to see that it's occasionally going black. But the light gun is not slow like that. So the light gun is actually seeing it change during the redraw. And we're going to need that later when we detect the timing to work out the exact white line. But a lot of the other times it'll be a problem. And so we're going to have to work around that and read in over a period of time and basically take the minimum value of that bit. So that's bit 3, the light sensor, and bit 4 is the fire button. So you can see I'm pressing the fire button here. And this emulator will actually, if I press the right mouse, will simulate firing off the screen. And that's so some games will use that as a reload technique. So that's quite handy, something worth knowing about this emulator. So anyway, so we've just got 2 bits that we read in from the port, very straightforward. So not much to worry about there. Okay, so that's our first example. We're just basically reading in from that port, and then just to allow it to be shown to the screen, we're waiting for it to change. We're resetting something called cursor X and cursor Y, but those are just my font drawing routines that are used by the monitor. They're not related to reading in from the light gun. So that's the first example of just reading in the port, so we can see what's going on. And now we're going to create the most unremarkable game in the history of the universe ever, called Chibi Shooter, and we're going to shoot some chibicos, or just one of them in fact. So let's just connect our joystick like on here. Here's our chibico, and now if we shoot, we can see we're firing away here, but we're missing the chibico, so nothing interesting is happening. But if we shoot the chibico, you can see the word hit appears on the screen. Now if we in fact shoot something that's not the chibico, now we should really clear our screen, but we're not. So if we shoot this, well, this here, if I just get it right, there we go, it's white when the chibico wasn't lit up, and so that means that we're probably pointing at a light bulb trying to cheat, so it's put the word cheat on the screen. So what are we doing here? This is the duck hunt routine. So basically we wait for the player to fire, we black the screen out, we scan the screen. If the light gun can't see light, it's probably pointing at the screen. We then white out the chibico, we scan the light gun again. If the light gun can now see white, well, that implies it's pointing at the chibico, or the player has moved the light gun and pointed at the light bulb very, very quickly. Either could be true. Now, if we'd got multiple enemies on the screen, we would need to flash each of them at once in turn to see which one of the enemies the player was shooting at. So this might work okay for a game with just 2 enemies, like your duck hunt. Not going to work very well for Operation Wolf unless you mind the screen flickering for an awful long time. Just depends on the kind of game you're trying to make. Okay, so let's have a look at the actual code that does this one. Well, first things first is we've changed the code that's actually reading in from the light gun. Now here's our new routine. So this is our test light gun routine, and the first thing we're doing is we're waiting for a V blank. Now all of our light gun reading involves changing what's on the screen, so we might black out the screen and then see if the light gun can see dark, or white out an area of the screen and see if the light gun can see white. But we're going to need to make sure that the screen is actually showing what we're expecting it to, and that means waiting for the start of a new refresh. So we're waiting for our frame there, and then what we're doing here is my routine will update this V blanked register in the zero page entry, rather, I call it a register. We update that V blanked entry in the 0 page once the randomize starts running. So we're going to wait for that to change to know that the V blank has indeed occurred. So that's what we're doing here. We're starting a new V blank, and then we are scanning, and we are taking basically the minimum value that appears in 4017, because if you remember, that light sensor will go up and down as the screen scans, and it's a low value of 0 that means the light gun has seen the light, so to speak. So at any time during the drawing of a frame the light gun sees light, then that bit will be set to 0, and that implies that the light gun is pointing at the target, whatever target we put on the screen. So that's how we're doing it. So this will wait for a full frame and read in the light gun for us. So that's what we're going to use. So here's the start of our Chibi Shooter game. We've got a draw chibico routine here, which is basically the same as in the Simple series. So if you don't know how that worked and you want to know, then go and check that out. Then we are just reading in from the light gun. Now at this point we're not checking the light, so we're just checking the fire button, and so we are masking out that bit there. That is bit 4 there, and that's the trigger, and if that's a 0 then the trigger isn't pulled, so we're waiting for the trigger to be pulled. Then what we do is we now black out that Chibi, which we're basically doing by setting all of the Chibi tiles to tile 0. And then we're running that test light gun routine, which will scan a full scan of the screen and see if at any point the light gun saw light. If the light gun saw light, that is bit 3 there, that bit I've marked L there. That means the light gun is seeing something that isn't on the screen. So maybe that player is trying to point at that light bulb. So we show that they're cheating, or maybe they're just pointing at the window by accident because they're a really bad shot. Either's possible, but anyway. So we know that they're not pointing at the screen at this point, and we give up. If we've not seen any light yet, we now white out the Chibi character to draw a white block around that character. And now we test the light gun again. And at this point, if the player's pointing at something that's white, they're probably pointing at that Chibi. So we assume that they've hit the Chibi. Now, if we've got a 1 in that bit, though, the gun hasn't seen any light. So we're going to just skip back to the start here. And we, at that point, would redraw our Chibi because the whole routine is going to start again. But if the player has seen light at that point, then they've scored a hit. So we're showing the hit message to the screen. So that's the simple way of creating a light gun game. As I say, you just black out the screen, check that the light gun sees black. You make your target white in some way. You check that the light gun can see white. And if it does, then you know they've shot that target. So that's how you do a game with just a few targets on the screen. Very good. That's the easiest way of doing things. What we're going to do next, though, is look at the more advanced way, which I think is quite snazzy, quite clever way of working around. Now, I do have to say, of course, it's not as good as the way the Master System does it and or the Super Nintendo, because those are pixel perfect, give or take. But you can get a much better than that simple duck hunt example, and you can see it just here. Now, basically, what we do is we start at the start of a new NMI at a V blank. We fill the screen white by changing the palette so all the colours are white. And then we start reading the light gun until it sees the white and counting as we do. And when the light gun sees the white, we then take that count and convert it to a Y line. And that will give us a vertical position that the light gun is pointing to. So we'll know how many lines have occurred. Now, that is good enough for a Y line, or approximate Y line at least. I'm working in tiles, but it doesn't help with the X coordinate. The Master System gets an X coordinate by having an actual hardware register that is automatically set when the light is detected. It's got dedicated hardware to do the job. The NES doesn't have dedicated hardware to do the job, so what we do for the horizontal line is what you can see here. Basically, when the player presses the fire button, a set of sprites are moved across the screen super fast, and that is detected once per frame. It will put the sprites in a position, check that position, move them along if it wasn't spotted, check that position until the light is seen, or the sprites have dropped to the end of the screen and not been seen by the light gun. So that is what we'd have to do, and that is pretty much what I've done in my code here. So this is the third scanning example. Now, there is a limitation of my example, which I will explain in just a moment. But first, I will show it off for you. So if I just go here and I select machine input port to light gun. OK, and now this is the second example. So now if I press fire at any position on the screen, the game will try and scan, and it will try and work out the position, and it will show it in the X and Y. And these are in a approximate tile-based position, so 0 to 31 and 0 to 30 vertically roughly. So if I, for example, press in the middle of the screen here, you'll first see the screen flash white as the Y scan's done, and then you will see a block run across the screen looking for the X position, and you saw it just there, hopefully. So you can see there the block is actually going past the cursor, and that's because basically the screen is being updated one frame behind, because the NMI is happening after the scan has been completed. It's then showing the next position that the sprite would have been in, but it is working. So if I press fire up here, you can see I've got Y equals 0 and X equals 02. If I press in the middle here, X is still 02 but Y is now 0B, and if I press down here, X is still 02 and Y is 1A, but if I press over here, X is now 1E and Y equals 1A. And basically you can tell we're getting an approximate position of the cursor. Now if I do something tricky like fire there and go fire off screen using the right mouse button there, you can see that the Y has been set to 1D, which is an impossible value according to this routine. The routine will give up if it's got to the bottom of the screen. And also if I trick it, if I press fire but then I move the mouse so that the cursor has never been detected, well, you can see we get very high X values. So this is actually just giving out of range values when something went wrong during the scan. So that's the way this routine works. Let's take a look at how it does it in the code. Now, the NMI routine is what we'll have a look at first. Now, the NMI routine is actually doing some other work as well. It's updating the tiles and the sprites. Now, the sprites, it's using a DMA to transfer a buffer to the sprite RAM, because we can only update sprite RAM during VBlank, and the tile map, we can't really update tiles except out of VBlank as well. So the tile map, it's updating up to 32 in a loop here. So we've got a routine there that transfers that data. But if our Lightgun Y has been set to the special value of 255, we're not going to do that. We're going to branch out to a subroutine called NMI Lightgun, and that is what we've got here. So this is a special Lightgun scanning routine. So to fire this off, we set the YPOS to 255, and then we wait for it to change, and when it changes, that's the YPOS that the Lightgun routine found. So first of all there, we're just decreasing the Lightgun Y here, and that's just to tell it that it's been started. That's so our other routine can check that if it wants. And then what we're going to do is we're going to set all of the colors to a special palette W, and that's just got all the colors as white. Fastest way of setting the entire screen to white, because we no longer need to check the position by moving any kind of block or anything, because it's the redrawing of the raster, which is a hardware process that we're now scanning for. So as I say, even though the viewer will never see that the screen is gradually getting white, it is, and the Lightgun can see it. And that's what we're looking for. So we've basically got a delay that it is the equivalent of one 8-pixel tall block or thereabouts. And what we're doing is we're constantly scanning in from that Lightgun port and waiting to see when the gun has seen the light. And until it does, we're just basically looping around here. Once we've got to either line 34, which is off the screen, or that the light has been found, we then jump down here. We're then just taking our Y value, subtracting 5, because there are 5 blocks that are off the screen. These are basically part of the VBlank. And this will give us roughly the Y position as a tile number. And then we're just jumping back to the end of our regular NMI handler. There isn't actually any time left to update the sprites, but the sprites probably weren't on the screen anyway. So that's the end of that NMI run. And we only do this when we actually want to scan for the light. So here's the start of the test code, and what we do is exactly the same as before. We're testing the bit here, that's bit 4 there, and we're just testing to see if the gun has been fired, if the trigger's been pulled. If it has, then we end up down here. We're setting that Lightgun Y to 255, which will tell the NMI routine to start the scan, and then we're waiting for that to occur. Now that will basically do the scan, and then we'll hand control back to us. And then what we're going to do is we're going to wait for VBlank again. The reason we're doing that is we need to set the palette back to what it should be. So that's what we're doing here. There actually wasn't time during the last VBlank in my testing to do that during the actual Lightgun scanning routine. So that's why I'm doing it here, but that will restore the proper colors for the screen. And then we are going to just check to see if our Lightgun Y was a valid one, and if it's not, then we are going to give up because we've been given an invalid value. But if we've got a value that looks like it could be a legitimate position for the Lightgun, then what we're going to do next is we're going to use hardware sprites to actually scan for the light. The reason we're using hardware sprites is we need to black out the screen except for a small area, and the easiest way to do that is to turn off the background, and that's what we're doing here with VDP registered 2001. We're just turning off the background but leaving the sprites on. And what we've got is we've got a routine called showgun target, and this will create the scanning block that you can see here. So that's actually a set of sprites. They're actually 8x8 sprites. You could use 8x16 double height sprites, but I didn't bother because it didn't make any difference for my code. So that is what we're going to use, and we've got a routine to do that called showgun target, and this will set up the sprites in a grid of 4x3 to make the test target. And it's setting those in the RAM within the NES RAM, and then they're being transferred by the NMI interrupt handler into sprite RAM. So that's why we have to wait for NMI interrupts quite a lot. So there we go. So that's what we're doing. Now we're using our test Lightgun routine, but we're not actually going to wait for a VBlank at this stage, and that's why this routine will always end up actually one frame behind. So it will be testing the last position that our showgun target routine set the sprites to, but that's not a problem. Then we're testing the Lightgun light bit and seeing if any light was spotted. If no light was spotted, we move the target across the screen another 4 blocks, another entire 1 unit basically, and we repeat until we either find it or we get to position 34, which is basically the end of the screen. If we find our target, then we are actually subtracting 2 from the X position. The reason for that is that basically the position, our X value will always be the next location of the target, and we're assuming the light gun's approximately the middle, so the middle is subtracting 2, and that is getting our X position for the sprites. So we've got the Y position from the NMI and the X position from moving the sprite across the screen. There we go. So that's all I'm covering here. As I say, there's lots of code here relating to how the hardware sprites work. But as I say, if you don't understand tile maps, hardware sprites, I'd suggest you look at the YQuest series, because as I say, there was 2 episodes there, one on an efficient tile map routine and one on a hardware sprite routine. And they are basically the code that I'm using here. So that's the best way for you to learn that. Now, one thing I will say is my code isn't as smart as the Operation Wolf code. The Operation Wolf code is very smart. Now, you will notice, if you look carefully, that when the fire button actually is pressed, if we just look here, you can see that there's a pair of sprites that scan across the screen. Now, what the Operation Wolf code actually does is when either of those 2 are hit, it will then remove one of them and see if the hit is still detected. And by a process of elimination, it knows that if it's still hit, then the one that it is still showing is the target. And if it's not hit, then it knows the one it just removed is the target. And so if they're pretty much halving the amount of time you have to scan across the screen by doing that. My code couldn't do that. It's unfortunately not quite as efficient because of the way it's waiting for NMIs. But I think my code is fairly adequate, at least, certainly as an example. So there we go. That's the end of today's lesson. As I always, I'm afraid I have to shill my book. So if you want to support my content, you can buy my book from Amazon. Learn Multi-Platform Assembly. It covers Z80, 6502, 68000, 8086 and ARM. It doesn't cover the NES Zapper, I'm afraid, but who knows, maybe one will one day. Anyway, if you've enjoyed it, please hit the like button and subscribe. And of course, go to the website, download the source code and make the most amazing light gun game you can. Thanks for watching today, and goodbye.